Well, hello everyone. Let's start with this webinar series today. Today we're going to talk about two ways DEM-FEA analysis for bulk material handling equipment. Our expert today is Prasad Abilala, and I'll be supporting in the background. If you have any questions during the webinar, please let us know in the chat, but also we will have a Q&A section at the end of the webinar.
Thanks, Cesar. Hello all. Thanks for joining today two-way DEM-FEA analysis for bulk material handling equipment simulation webinar. I am Prasad Avilala from Altair Engineering, India. Basically, my role is EDEM Global Technical Support Team. So today, the contents which we are going to discuss is about challenges of bulk material handling equipment, EDEM-OptiStruct two-way coupling, and at the end I will be demonstrating one of the example case, a live demo, like setting up how to setting up the SimLab setup and EDEM setup to run a two-way coupled workflow.
Thanks very much, Prasad. And before we started with the webinar and Prasad presentations today, I have two questions for you.
Thanks, Cesar. So we'll start with understanding what is the challenges faced by bulk material handling equipment manufacturers. So in general, manufacturer of heavy equipment industry people will be faced with a wide range of challenges to meet the demand of the market, and to stay competitive manufacturer and need to be continuously improve the performance of their design. Okay, so to meet, just I'm repeating my statement, to meet the demand of the market and to stay competitive in the market, manufacturers need to be continuously improve the performance of the design and efficiency and reliability of their missions, but also deliver product quickly while ensuring product innovation. This means they have to shorten the design cycle, and getting the right things at first time should be the critical aspect. So one challenging aspect relates to the range of operations and conditions that missions have to perform in, while another significant aspect is the range of material that machines have to deal with. We will, these are the major challenges will be bulk material handling equipment industries was facing today, and we'll see most of the applications or most of the challenges how we can able to address with EDEM with two-way coupled simulation. So when we will see in this slide about EDEM-OptiStruct two-way coupling benefits. So in general, before DEM evolved into the market, so they were the industry people used to use the concept of hydrodynamic principles to design the structural equipment. So by gaining EDEM as a bulk material software, so which evolves more realistic loads rather than the worst case and hydrodynamic scenarios. So now when you couple EDEM with OptiStruct, so which enables the industry people to more closely or more realistic structural simulations can be performed, which enables more optimizing the designs, which in return they can expect the more saving of the material Also, due to this, EDEM to OptiStruct two-way coupling, advanced simulations and complex scenarios can be solved. And because of this numerical simulations, the end we can see the testing, physical testing and prototype manufacturing can be reduced. So with the two-way coupling, we can able to get a very greater insight into the equipment performance. So these are some of the key benefits which we can able to get it from EDEM OptiStruct two-way coupling. And coming to the the multi-physics capabilities, when EDEM to be integrated with, there are different simulation products. When it take EDEM can be coupled with computational fluid dynamics, such as Occisolve Fluent as a two-way to study the bulk material behavior under the influence of fluid. At the same time, to understand the kinematic definitions, or you understand more about joint forces and other structural behavior, EDEM can be coupled with multi-body dynamics, such as multi-body dynamic solvers such as motion solve, atoms, and Rickardine as two-way. And prior to this, new capability coupled with EDEM and OptiStruct, earlier we have EDEM coupled in for FEA solvers such as Abacus, OptiStruct, and ANSYS as a one-way. So now the new capability which we are going to discuss is EDEM with OptiStruct two-way coupling. So, what are the advantages we are going to get with respect to, either a one-way coupling or sequential coupling in terms of, two-way coupling? So, the first and foremost advantage, if you see, when some of the applications where, after, material cutting, there will be material flow over the equipment, so which also plays a crucial role in generating a large forces and stresses, or even wear about the equipment. So such behavior to simulate, it doesn't possible with either a sequential coupling or a one-way coupling. So this is where the primary advantage we can get is like to simulate the stresses strain as a continuous time dependent medium. And the second advantage is like we can able to get geometric deformations, where you can compare these geometric deformations even with multi-dynamic solvers, where all multi-body dynamics, most of the multi-body dynamic solvers are linear in nature, where the large deformations cannot be possible or simulated. So in such conditions, EDEM plus OptiStruct two-way coupling will enable large displacements, which you can able to see. The structural deformations are very large, and even earlier there was no geometric deformations are possible in EDEM. So the left side video which you see is from the EDEM, and the right side video which you are seeing here is from the OptiStruct. So this is the second advantage which we will get it from two-way coupling. So the next one is in terms of the power calculation, or the force as an output to require any of enforced motion conditions. It's easy to obtain from FEA solver as a reaction force, which you can see if you apply as an enforced displacement as an input, which in return we can expect a reaction force, which is the force required to move a complete system can be get very easily. And the last and the much more valid and important advantage is like life of an equipment, which can be able to predict with a time dependent loads. For example, if you see any structure, if you want to perform a life under the bulk material equipment, it was very difficult earlier because it was used to perform unit load case and then assume certain loading cycles to perform the life. But now with the enabled two-way coupling, where we can able to run the simulation with a realistic loading condition and try to take the results, either the linear results or non-linear results, and perform either a stress-based SN based approach or strain-based approach to calculate the life of an equipment. So these are the key advantages we will able to get it with two-way coupling. So now to understand the two-way coupling workflow, here is the slide you can see. From the above, the SimLab GUI, meaning SimLab is the interface or GUI interface, to run a EDEM plus OptiStruct two-way coupled simulation, where the pre-processing work will be set up from the SimLab GUI, and solver is from OptiStruct explicit solver. From EDEM, as you all know, bulk material simulation software, whereas OptiStruct explicit is an finite element based solver. So to start with FEA simulation, we need the CAD model of the equipment. For example, in this case, a tunnel bit, and we'll try to mesh. Depends on the criticality of the simulation. And then once you mesh it and establish the necessary connections and then contacts, then we have to define a motion or the force as an input condition, and then there will be a simulation setup. This is from the FEA side, whereas the input condition are from the EDEM side is to create or to given a material bulk material properties and interaction properties between particle to particle and particle to equipment, and then we have to define a particle shape, size, and its distribution, and then we have to import or create a CAD model in EDEM. So which will be setting a preprocessor or the input condition from the EDEM side, along with contact models or the physics models to be defined as an input. So as of these two steps, like FEA and EDEM, will be setting up independently. Until these steps, there is no connection between EDEM and the OptiStruct. Because from FEA side, separate model building, and the EDEM side, it will be separate connection. But now the moment once you start solving, so the coupling will exist, and we will see how the coupling starts in after some time. So once the two-way coupled simulation solve, we will try to find results from either FEA side is elemental stresses or strains, and the reaction force, displacement is some of the key outputs from FEA results. Whereas from the DM side, the particle, bed, and then wear or some of bonded. If, for example, in this case, the bond status, whether it's the bond was broken or it's established, is some of the output from the simulation. So coming to the workflow schema of EDEM-OptiStruct, how this coupling scheme works between EDEM and OptiStruct. For example, if you see a simple example where there is a plate is experiencing the force from the particle. So how this coupling works? So you can take OptiStruct is one of the solver and EDEM is one of the solver. There are two different independent solver. How this works is, so when the particle first EDEM triggers the forces of the bulk material onto the geometrical node, that is what we are calling as a nodal forces. From EDEM, the nodal forces are communicated or transferred to the OptiStruct, and then from the OptiStruct, the nodal coordinates will be transferred to the velocity. So here, prior to this, transferring the forces, there might be a question arises: what could be the geometrical differences in, EDEM and OptiStruct? So here, there won't be any geometrical differences, because when the coupling or the simulation starts, the geometry has to be transferred from, our OptiStruct or SimLab GUI to EDEM. So that's where the nodal forces we are saying, as the mesh and nodes is in line with EDEM and OptiStruct. So that's where from EDEM nodal forces will try to start transferring, and from the OptiStruct, in response, it transfers back to, after solving OptiStruct FEA simulation, it gives us an output or input to the EDEM is like new nodal positions and the velocity. We'll see how this scheme works as a coupling. So the same under the same case where the material is experiencing bulk material forces on a geometric plate. So first EDEM starts. That's where this bottom line, you can see it as a EDEM, and the top line is OptiStruct. You can follow this arrow mark head to the directions and the number scheme. From the first step, Tn indicates the initial time step. Tn plus dt is the incremental time step. So from the initial, the material EDEM generates the particulate material with until the next time increment of EDEM, that is Tn plus dt. Once it reaches Tn plus dt, the nodal forces from EDEM, it transfers to OptiStruct. That's where you can see forces will be transferred to nodal forces to OptiStruct, and then OptiStruct perform FEA calculations until the new time increment of OptiStruct solver, that is Tn plus dt. dt is the OptiStruct time increment. We will discuss this OptiStruct and EDEM time increment when we are when I was explaining the live demo case. So and then from the again OptiStruct, it transfers the nodal coordinates and velocity of the new time increment to the EDEM. And again, EDEM starts the same step of one. That's for the new time increment. It starts particle generations, and the force exerted by the particle will be again transferred back to OptiStruct for the new increment, and then OptiStruct solves to another time increment of, that is Tn plus 2 dt. From there, OptiStruct transfers new coordinate or position of the node, and then it transfers the velocity. So this is the coupling scheme works EDEM plus OptiStruct as a two-way. Coming to the for example of the time step, you can see the time step in general in OptiStruct should be very lower. We will see why it should be lower as well. What happens if it is higher side. We will discuss from one of the simulation output file. And we all know from the DEM, the time step is used as a time step, and this depends on different parameters such as minimum particle radius and solid density, and as well as the shear modulus. So the ratio it gives here for in this, these are some of the example case for understanding purpose. The ratio you can see 250. There was no ratio that we should follow as of now. Just to demonstration purpose, it was shown to for understanding purpose of what is the time increment we are following. Now we are going to see a few example cases for the next few slides, where earlier, as I mentioned earlier, there was no geometrical deformations captured in EDEM. earlier, as we all know that EDEM works based on the rigid body principles. So where the shape change or deformation of the element, a geometrical element is zero. So, but now we by coupling, we were seen one of the example where large deformations are possible. So here, one of the example what we developed is like filling of the material in a bag, where the in OptiStruct we modeled the bag as shell elements, that is 2D elements. Under the bottom, it's constrained all DOF. On the top, as it's we are trying to hold, so two DOFs are fixed, and the third Y is free to try to allow certain expansion and movement. And here there was no other forces are applied from the over the bag except the bulk material loading. So you can see how the geometry deforms. Here we are not, I'm not, particles are hidden, but you can see once the material is loading how the geometry is deforming. This is an EDEM simulation, not FE geometry or FE results. So you can see clearly when the material is loading, the geometry is trying to deform like expansion of the balloon kind of structure. So this kind of structural deformation, now we can able to easily reproduce with respect to EDEM and OptiStruct two-way coupling. And we can see here, these are the left side results is about EDEM, and the right side is with FEA results. You can see the particle loading into the back. So how it loads and try to deform the structure due to the self weight of the material. So this is one pass, and the second pass to show the other side deformation. The material is loaded in other direction, and try to see the deformation due to the material movement and as well as material geometrical deformation. So from the FEA, we can able to see the geometrical displacement as well. So the structural deformation can be able to predict it. So this is one of the example where we can say that the large deformations are possible with respect to EDEM and OptiStruct two-way coupling. So the second case is it's loading and unloading of bulk material, where this exercise intention is to demonstrate the key feature of how to make the material to be rotated, the gate which to be rotated. So to model this, there is a box structure which is modeled with tetrahedral elements, and the gate, what you are seeing, thick blue color. Also, it's a solid part and model with tetrahedral elements, and the bottom plate just to hold the material for to visualize the material is holding on the plate. So these are all modeled with tetrahedral element, and the bottom face is fixed. Bottom face of the rigid, and as well as the bottom face of the box structure is constrained in all DOF. And then here the red line which is shown here is applied with enforced displacement, and the black line axis which indicates the about the enforced displacement is rotated about this black line. And also a hinge joint is modeled between the blue part and light cyan color part. So these two parts just rotate about the black line axis with the help of hinge joint. So now we will see how the EDEM and OptiStruct two-way coupling helps to unload the material. So this step we are loading the material, and in a quicker action, you see we are trying to unload rotate the gate in very fast, or in a very short time, because this is what in a realistic case will happen, and rest all with how the material allows to fall down. So this the intention of developing this use case is, under the small models, we will try to replicate any kind of new mechanism to understand and implement in the large scale system. So here, then this about the EDEM results. And next, coming to the OptiStruct side, you can see there is a displacement, how the plate was rotated, which shows the rotational displacement, or you can see the displacement magnitude of the plate. So the third case is about the drum truck, which is an extension of previous case, where we used a rotational motion to obtain hinge joint. So similar to that, we used the hinge joint, but there are certain key aspect in this model. What is the key aspect? First thing is, like, we know the drum truck body is very massive, and there is a complete vehicle structure. So it is not case that we cannot able to model a complete vehicle. It is possible, but it takes huge computational time, because of increased degrees of freedom for the simulation. So to reduce what is the model content we need to consider, whether only body itself or any other structure, we need to implement it. So that is the first step, key aspect to consider this use case. So that's where if you see the load body, tailgate, underneath there is a mounting bracket structures, which you will see in the next slide. So those are the minimum components which we need to consider. And then the about the hinge joints, how many hinge joints to be modeled, how that is the key aspect, because between tailgate and truck body, we should define a hinge joint on either side of the mounting locations, which you can see left and right side. So two hinge joints. And how the loading of bulk material, let me talk when I was showing the animation. So now here all the parts are modeled as a first order tetrahedral element, and you can see the bottom parts which is considered for the numerical simulation of EDEM plus FEA co-simulation, is these are the mounting brackets, because we need to consider certain additional parts to avoid localized displacement and stresses. So that is where the extension to the underbody, truck body, these are the mounting brackets is considered. Even still we can extend it, but the computational time will increases. So here the blue bar mounting bracket, which was connected at the whole structures, is constrained in RDYF, and the axis which mounting bracket 2, you can see with red and green rigits, which was connected and created with a hinge joint to rotate when we apply a load over the truck body. So we see this response from the simulation EDEM plus OptiStruct two-way coupling. So you can see here the massive load of 25 tons is loaded with very short time. See, that's where we can still see the jerk and very in short time, because of to reduce the computational time and the loaded the material, but still the solver is more stable in such a way that it withstand the shorter shocks because of explicit solver. And because of the weight of the self weight of the particles, and it which impacts the tailgate, allows the tailgate opening, and which unloads the material from the truck body. which is an extension from FEA. From the EDM, we can able to simulate loading and unloading. I don't want to duplicate the loading and unloading, the mass flow rate and the traditional workflow. Just I want to demonstrate what an extension apart from the traditional loading and mass flow rate, where what the new capability, what we want to demonstrate. That is the only I'm concentrated here. Apart from you can check it in the Altair community forum, where the drum truck load case, the traditional outputs are can be requested. But with the two-way coupling, the major focus is we can either plot one versus stress if it is a linear, or in non-linear, the strains can be plotted. And for both tailgate and truck body. So this is the third use case. And the final one, and which we are going to discuss, is tunnel bit drilling. Now I'm going to demonstrate on the live by importing the setup into SimLab and as well as EDEM software. Before demonstrating the example, just want to give you an heads up that the two-way coupling which we are discussing now, which is available as a beta version from 2024, which is expected to release by mid of May, and we can you can able to test it, and we are happy to receive feedback from you people, where which you want any specific new functionality. Please share us your feedback. But at the same time, the official two-way coupling build will be tentatively try to release in 2024.1 in the month of August. So this whatever the 2024 version which you are going to receive will be a beta build. Where there from the solver front there was no difference with final version and beta build. The only with the extension, what we are trying to see is we want to test from from the users and get feedback to get more simplified options. That's all. So let me go back to the setup. So this is about our SimLab, which was my old beta version, but the new beta version is much more simplified. We can call it as these are the ribbons, and to reduce the webinar or the time based on the mindful of time, I am trying to reduce the simulation setup for the meshing. So what I will do is I will try to import an FEA setup file, meaning elements already meshed model, and try to demonstrate what is key aspects which you should taken care while setting up the simulation in the SimLab. So the first and foremost step, what I would request is I would suggest go through what is the model first. If it is a geometry model based on the unit length unit, you can keep it the system. For what is the file FEA file which I'm trying to import has a unit system of a millimeter as a length, mass is the tons, and force is in newtons, and the time is in second. So the first step to import FEM file is file, import. You can see whether there are different options like importing the hypermesh file, or CAD file, or if it is any setup file, you can click on the solver input file. So where we can see there is a FEM file which is an OptiStruct file, and which already says the unit system is millimeter, ton, newton, second. So I was maintaining the same unit system. Otherwise, what happens is the file which imports will be converted into the new unit system what is defined here. So that's where I was maintained first step, imported into same unit system. The second step you should measure is the model is imported as per your expected dimension. So these are the second check I would request the users to follow. And the third one, so this is a browsers for options to switch over from one setup to other, where you can see this is about the model setup where the match CAD and elemental data will be there. Here is the option for material or properties. So where there is a standard material database, or you can also create your own material. And then here you can check what is the material is assigned by right click, select the component. This is the body option, and select as the right material. Steel nonlinear is the material is assigned. You can double click here, and you see the properties. Density is in the ton per meter cube. Young's modulus is the different value, like 6500 MPa. So where I would request users to follow units of pascals, so you can convert because EDEM follows the Pascal units and it should be consistent. So where what I would recommend is, now you can change the units to meters, kg, Newton per second. So then you can see here automatically the material properties get updated. Even if you see the measure the data of the length of the model, it converted to meters. So which is the fantastic option in the SimLab. Whereas if you want to manually do, it takes minimum 30 minutes to 1 hour, and there is a possibility that manual errors can happen without disturbing your mesh quality and any manual errors. It was set up quality very fastly. Okay. And see here there will be some default load case will be created. This is the option where you need to set up, that is the solution. So try to delete the default option. And the first step is you should define an explicit load setup. For that, you can go to solutions, and then you can go with structural simulation and create it, or right click, create a solution. By default it goes to explicit dynamic. So this is the solution type you should use for EDEM plus OptiStruct two-way coupling, where you can see if you want to run other cases only SimLab, there are other solution types, linear, non-linear, and other cases. But for EDEM plus OptiStruct, two-way coupling, explicit dynamics is the solution you have to create. And the key point here is you have to select the bodies which are all to be a part of the simulation. So you can use left mouse button to drag and add it. These are the part names. If you observe from the front window, these are the two part names which is added to the solution browser. So now if you click OK, it creates the solution. Now the second case is material is, see, meshing is there, material is assigned, properties assigned, and then we have to define the load definitions. So for that I will use constraint. I want to fix all except translation Y, all other DOFs I want to constrain on this particular node. How to select this particular node? This is selection browser, where you can go to here, and this is a rigid node, center node, which I want to select it. See, you can see the highlightation of node. Select that and click OK. So which applies a constraint. And if you want to change any DOF, double click on the constraint. It enables the GUI for selecting the option. You can change any point of time. So this is one of the constraints. I defined DOF for constraining the model, and now I want to define a motion. So I want to define a linear translation motion. So that comes under the enforced displacement. Here it is a time-dependent displacement I have to provide. Whereas here there is no time-dependent motion. How to define is you can select, in y-axis, you have to define as a one instead of, because it's in meters. What I would suggest is like a 0.001 is the scale. Choose a time dependent table where you need to create. It opens to the new browser, and I want to create first 00, and in 1 second, if you enter at in 1 second, from 1 second also 0, and then for 1 to 2 seconds I want to move the geometry by 20 mm as a forward motion, because and then the second I want to bring the model by 5 mm back, so that is like a 15 mm position. So similarly you can increase 20 mm, so which is 35 mm, and then you can after increase, and you have to bring it back 5 mm back, so which is the 30 millimeter, and then you need to add another 20 mm to forward direction, so 30 plus 20, which is 50 mm. And this is how the motion you can define. But I have entered the values in positive direction, but I need a motion in the forward negative direction. Why negative direction? So what you can do is you can apply a minus sign before this magnitude. So this is the scale which it multiplies with that time. So now, what is the where I have to apply this enforced consent is still again I have to define on the node. So I can go and select here of the center of the rigid element, click on the node, and it will the apply and the OK button will be activated. Then click OK. So now the constraints and the displacement or motion is defined as a setup of explicit simulation is defined. Now, the controls we have to define it. So right click, define a solver settings, and then here the T term is nothing but what is the simulation time you want to stop it. Maybe you can say here, sir, 6 seconds. And if you want to check the solver elemental quality, you can keep yes. If you don't want to, if the elemental quality is bad, to ignore the quality check, keep no. And the second one more is if it is hourglass effects are there, if it is solid elements, so hexa brick elements, then you can use the appropriate hourglass controls. For explicit time scheme, we would recommend to use minimum stable time increment, and this is the key option in for running the simulation. So one is the scale factor of a stable time increment you can use, but the minimum time increment we should start always. I would recommend 1 e power -5, sorry -7. I will explain why this is -7 is the time increment. Why not higher, or furthermore I will explain in when we go for the presentation again. So once you define all these settings and quickly say OK, and then again go to solver settings and add result request. So whatever the result request you want to add it, you can add here. This is about the time interval. I want to write every result 0.01 second. I want to results request to be added. By default, there are certain results will be selected. I would request you can check and apply if the all necessary results are outputted. The next one is the key, one more option, that is format and execute option, where please check that the unit which you chosen, and in the format option both are same and consistent. So else it gives again wrong units for while exporting the deck. And the next one is if you are using multi CPU, then you can use number of processors, how many processor you want to run the simulation. So with this, the explicit, sorry, I by mistake I have not clicked this. So with this, setup, explicit simulation is done. The key aspect is now co-simulation creation. So how to do that is go to solution. There is a co-coupled solution option. Click this, and now here is the ribbon of what kind of simulation you want to select. Here is the structural plus EDEM. Click this, whereas in the latest version it comes as a beta here, not in the header. You have to select the faces here, okay, because this will be acting as a coupling interfaces between EDEM and OptiStruct solver. After selecting all the faces, click OK, and then the coupled simulation will be defined. So when you say tick coupled simulation with bold letters, which is the current simulation activeness, okay, under the settings, right click, solver setting, use coupling time step. So I would request the minimum, as explained about the time step exchange the data. I won't recommend any time step larger than zero point 0.01, because there will you can see some adverse results. So lower the time step, it's always better to get more accurate results. Once you define the coupling step, click on OK. So with this, the simulation setup is complete. So because as the time is up, I'm going to quickly wrap it off with EDEM setup, where I have defined already bulk material properties, particle and its size distribution, all details, with the physics model, bonding V2 model with predefined properties are chosen. And then now I need to import the equipment, where already I have created some geometries, which I'm going to import the CAD into the EDEM. So the CAD is imported, and this is the factory which I want to create it, the particles, and I'm creating a factory definition where the dynamic factory I want to create. Just to run is a small case where I want to create a 30,000 particles, and with respect to time 50 per number of particles per second, I will give 50,000, and I will give a small velocity in z direction of 0.2 meters per second to create particles faster. And then you can save this, and based on your properties, you can go lower time step, so that the model will be stable. But here what you need to define is, as it is a bonded model, you have to define if the time step at which bond has to be formed. So you can based on material creation, I would suggest with my definition, I am trying to create the bond at 1.5 second. So before that the material creates, and then it allows to settle down and then forms the bond. And there is a whole small feature I created to remove after the material is stabilized and forms the bond. So I will try to define a linear translation motion from 1.5 seconds to within a short time 1.6. I'm going to define a huge velocity to move very in x direction, to allow the geometry to move, so that it give access for the drill bit to drill and material to be evacuated. If it doesn't move this particle after broken, the bond broken, it the particle still exists, and it creates unnecessary behavior of the material collection. So once this is done, just enable the simulation. To show how the coupling starts is, if you start, just you have to activate this simple coupling button and go to SimLab. You should update here, right click, just click an update button, so that what happens is the simulation first, from SimLab, the geometry it transfers to EDEM. So it just first checking OptiStruct explicit solver as a preprocessor. See, now the geometry is transferred from in the creator window, and then automatically it switch over to the simulator and trying to run the simulation. So as mindful of time, I go for the presentation when it is the model is running. So the key aspect which to be monitored, if you remember, I was mentioned in SimLab, that time step DT min has to be chosen very low value because the mass error in explicit solver plays a very key role because if your time step is larger, it will try to add unnecessary or artificial mass, which makes your system, increase the larger mass, because of which I know unrealistic behavior and results will be seen. And you see, depends on the time step, it tries to exchange the data about what time EDEM start the simulation, and then it ends the simulation. So this is the mass ratio which we should be properly check, and until less than 5%, whatever the mass ratio which is out file of FEA solver, which it writes, it will be in a non-percentage, means you have to multiply this value one with 100, that is 1.628 e power minus 3 multiplied by 100, which is comes as a 0.16 percentage, which is less than 5 percentage. So it is okay to get good results with this kind of mass ratio. So from the simulation results, you can see this is about the drilling of cutting off the bulk material, and this is about the bond status once it tries drill the material due to forward and backward motion. You can see how the bonds were broken. This help us to understand the material movement as well, removed after the cutting. This is where I was given a motion to the plate to evacuate the material after drilling. So bond status 0 means it doesn't exist. Bond status 1 means it bond created. Bond status 2 indicates bonds are broken. Now this is about some of the results from EDEM, where we could able to understand the wear from relative wear physics model. And here you can see from FEA, we could able to see the the displacement on the rigid model, and also we can able to see due to enforced displacement what is the reaction force obtained from the co-simulation, and some of the von Mises stress which was low, and the here is the critical location. And to simulate life and damage, I was used Altair Hyper Life, which is a fatigue based solver, and default stress life curve was used to predict the life, which shows higher life means it's almost infinite life because the stresses are very low, and the material SN curve was very yield limit and endurance limits are very high. So that's the reason. But the location what with respect to stress and the life which gives was matching. So that's where only to get good correlation we have to use a appropriate material fatigue curve data. So in summary, EDEM plus OptiStruct two-way coupling simulation allows us to analyze the forces acting on equipment accurately, and as well as it improves the design of component by forecasting the hotspot stress regions, which can be predict structural strength and durability of the equipment, and also it improves performance of equipment, and due to virtual test under the different material. I solved one of the material condition. You can perform different material condition and try to get a different performance under the different material condition. So these are some of advantages we'll get it. And just to summarize the key point about the coupling, we will be getting a beta build in the mid of May, which is in the version of 2024. But official release version will be tentatively in August 2024 is the deadline. That's all from my side. Apologies for taking more time because of the demo case. I would request Cesar, please open for a Q&A session.
Yeah, and thank you very much, Prasad, for the presentation.
Thanks, Cesar. Thanks for your support. And is there any other further questions?
So there is a couple of questions. I can answer those ones. So it's about the EDEM simulation size. Remember that the EDEM simulation size will depend on your particle size and also on the number of particles that you have. So the smaller the particle size and the larger the number, then you will have more contacts, hence large simulation files. For the recommendations, what you can do to speed up your simulation is in community. But basically, these two factors, number of particles and the size, that's key in your simulation. So I think we can leave the webinar till this point. In the future, just to let you know that we run EDEM webinar series roughly once a month. Goodbye, everyone.
Thank you all. Have a good day.